enabling the intrinsic robotic sense of touch without use of any artificial skins or tactile instrumentation can revolutionize physical human-robot interaction. Based on high-resolution joint force-torque sensing in a redundant arrangement and fully integrated within the robot mechanical structure, multiple simultaneous contacts can be robustly identified and localized in real time, which can be achieved dynamically through the entire robotic structure. Through a momentum-based monitoring method to purely extract the external physical interactions, we were able to let the robot sensitively feel the surrounding environment and accurately localize touch trajectories in space and time that have been applied on its surface by a human. Contacts can be applied to arbitrary places on the robot body and irrespective of the joint configuration. This is enabled by the underlying fusion of multiple sensor signals by means of the dynamically decoupled momentum-based monitoring approach. This makes the estimation of contacts independent from the robot's configuration and unaffected by singularities. We shift the scope of using contact forces applied to a robotic structure beyond their conventional use and present an intuitive method for physical human-robot communication and interaction by simply touching the surface of the robot. Thanks to the effective fusion of model-based and machine learning algorithms, we can use the whole body of the robot as a tactile sensor. Furthermore, we show that our concept of the so-called virtual buttons can implement a tactile communication link in a straightforward fashion, including switches and slider bars, which are complementary to speech, hardware buttons, or control panels. The buttons can be freely designed and attached to the robot surface and directly mapped to motion commands. This opens up new opportunities in terms of intuitive and flexible interaction between human and robot. Moreover, these interaction elements can be placed, moved, and configured in arbitrary locations on the robot surface. The intrinsic sense of touch we proposed in this work can serve as a basis of an unexplored category of physical human-robot interaction not yet possible until now, enabling a shift from conventional modalities toward adaptability, flexibility, and intuitive handling. Our proposed human-robot communication link will also be established and active during highly dynamic motions of the robot. This is due to the precise estimation of external interactions using an internal dynamic model in combination with a sensing redundancy, which in turn further improves the overall accuracy. Our methods allow the recognition of touches applied to the robot surface through machine learning techniques. Manifold learning was used to unfold the written context on the curved surface and further processed with a rotational invariant convolutional neural network. The recognized context was mapped to high-level motion commands. As a matter of fact, our proposed technology can serve as a basis of an unexplored class of interaction modalities between humans and robots in the future.